Okay, great. Hello, everyone. Welcome to DFI's Impact webinar. Webinars hosted by DFI's Driven Pile Committee to highlight developments, current practices, and case studies focused on driven pile foundations. If you have a topic that might benefit this group, please reach out and volunteer yourself or volunteer one of your colleagues to present. My name is Travis Coleman, and I work for GRL Engineers. Just quick housekeeping stuff. All attendees will be automatically muted during the presentation. If you have any questions, please use the chat function within the meeting website or the webinar website. I'll monitor those questions and we will ask them of Dr. Coffman as time allows. So our presenter this month is Dr. Rick Coffman from the University of Arkansas, talking about drag loads and down drag on driven piles. I'm really excited for this. I got the chance to have a small part of his research, and I got to spend about a week with him out in Arkansas. So I'm really looking forward to seeing some of those results. So that is it. Rick, it's yours.
Thanks, Travis. Appreciate the introduction. As Travis mentioned, my name is Rick Coffman with the University of Arkansas. Just a brief background. This is going really fast for some reason. Hold on just a second. All right, I've got control there. Thanks, Kevin. At least I think I do. Yeah. So when Travis first asked me to do this, he asked me to talk about some work that I have going on for the National Cooperative Highway Research Program that we're trying to revise the specs for downdrag and for drag load. That's found in Section 3 and Section 10 of the AASHTO code. Section 3 is the loads, and then Section 10 is the resistances. Unfortunately, that project's not completed, and so I can't talk about the results from that. However, at the very end of this, for that project, we've developed 8 design examples. I can't talk about those, but I developed an additional design example that I will talk about at the very end of it, at the very end of the presentation, that is. And so what I'm going to talk about is the work that we did here in Arkansas, in which we drove single piles. We put charges around them in the soil, set off the charges to liquefy the soil, and then monitored what happened with a dead load. And so we'll talk about that design example. Just note that these views that I've expressed in this presentation are those of my own. They're not of any entity that's funded this research, and so just take that as a disclosure. So looking at this, the hypothesis is that if liquefaction happens, there will be some down drag and drag load that develops. The site that we're looking at in Arkansas, it has a clay cap. So the top 20 feet roughly are clay, and then there's liquefiable sand deposits below. And so we wanted to investigate what happens if liquefaction does occur. Does the clay that's on top grab onto the pile and cause drag load to develop? And then also what's the influence from the down drag that happens with that? And so what we did, we installed different foundation types. And so for this project, there were already some drilled shafts that were installed. There were 2 4-foot diameter shafts that were about 90 feet long, and then a 6-foot diameter shaft that was about 74 feet long. And then we came in and we put in some piles. And so we drove pipe piles, 18-inch pipe piles. We drove H pile, 14 by 102s. And then we also drove some precast concrete piles that were 18-inch square. Then we did the full-scale blast-induced liquefaction around the piles to see what happened. Each of the piles were instrumented, and so we were able to identify the effects of the liquefaction-induced down drag and the drag load that would develop. And we wanted to evaluate the neutral plane approach. So the neutral plane approach was that developed by Ph.D, and we wanted to identify if that approach could be used and if it's what should be used for this type of analysis. So looking at it, just a background on down drag and drag load, on how it develops and what it looks like. If I have a foundation in the ground, I apply a top load. So in this case, I'm going to mention the unfactored top loads applied to the top of the pile. That top load needs to be resisted, and so we have skin friction that typically resists that, and we also have some in-bearing down here at the toe that would resist that. In the event of in the event of an uplift foundation in which we're trying to resist uplift, you have some force acting in the upward direction. That force is acted against with skin friction acting along the pile. And then we also have some suction type of a toe bearing resistance that would happen at the toe of the pile. So both the downward and upward mobility of piles, whether it's in a compression or a tension type of a state. So if the soil is expansive and it moves up on the pile, that could cause resistance to develop along the pile as well, and we would have negative toe resistance. And so we're looking at how different types of foundations would react, whether we have moving soil, moving foundation, or the like. The last case is the one that we're really going to focus in on. This one, there's a downward movement of the soil, and we would think that we might have some negative shaft resistance that could develop. And if we did previously account for positive shaft resistance, like we normally do in a compressive case, and then we get movement, we might not have as much resistance available to us. And so we need to take that into account. So the last case that's shown on this slide on the right-hand side, that's the case that we're going to focus in on for the remainder of the talk. Going from both positive shaft resistance as designed to possibly some negative shaft resistance that develops as associated with ground movement. So looking at the neutral plane approach, the way that we can go about developing that is that we can plot our negative skin friction as a function, our unit skin friction as a function of depth. And so if we look at this, my resistance curve would be how much in-bearing I have at the toe. And then I would add on the unit skin friction cumulative from the bottom of the pile to the top of the pile to find out my amount of resistance that's available to the pile. For the load curve, I would start with, sorry, that's my resistance curve. For the load curve, if I did have some soil sediment, the load curve, sorry, I'm not getting to my curve yet. Taking too many steps with this animation. Okay, if we do get some soil settlement, we could have negative skin friction acting along the pile and then positive skin friction acting below this depth of the neutral plane. And so what that would look like if I have all of this animation done is I have my load at the top, and then I'm going to sum up my resistance unit skin friction along the length of the pile. And so for the resistance curve, as is identified, it's the toe in-bearing capacity plus the sum of the skin friction. And then for the load curve, it would be the top load, unfactored top load, plus the unit skin friction as a function of depth. Where those two curves intersect is what we would call the neutral plane. And so anything acting above the neutral plane would be negative skin friction. Anything acting below the neutral plane would be considered as positive skin friction. And looking at that, the amount of drag load that would develop on the pile would be considered from the crossing point of the load curve and the resistance curve, and then I would take that value and subtract out the top unfactored top load to find the amount of drag load that would develop on the pile. And so we have this R max and QSR, that would be the total difference, and that would be the drag load. What's interesting is that we can also look at this in settlement space. And so if I take the soil settlement that develops and plot that as a function of depth, and I also plot the pile settlement as a function of depth, where those two cross, that should also be the location of the neutral plane. And these two neutral planes should coexist. So whether I do this in terms of load or whether I do this in terms of settlement, I should get the same location on the neutral plane. Note that this foundation settlement curve, the reason why it's kind of bending like this is because there's elastic compression in the pile. And so as we have more load in the pile, then we will have more elastic compression. And so that's why there's some curvature to this foundation settlement, or the pile settlement in this case. What we would do with these two curves is that I would take the minimum of my resistance and my load curve, and I would call that a combined load and resistance curve. And so for this diagram that's shown here, the curve that would be used to find the elastic compression in this pile would be the curve that's the minimum. And so I would be on my load curve until the neutral plane, then I would be on the resistance curve below the neutral plane. And then just for clarification, because the current code, as it was mentioned in section 3 and section 10, there's some nomenclature differences. And so down drag is always the amount of settlement. And I would specifically say that down drag should be the amount of settlement at the neutral plane. So how much the pile and soil have moved at the location of the neutral plane is the definition of down drag. And then drag load is the amount of difference between this maximum in the pile and the amount of unfactored top load that's applied to the pile. So to investigate this, as I mentioned, this is a site in Turl, Arkansas. It's in the interchange between I-555 and now I-55. It was US 555, but now I-555 and I-55. So this is coming out of Memphis, going to St. Louis. That's I-55. And then this ramp is coming from Mark Tree, Arkansas, and then coming to St. Louis, Missouri. We're right in the interchange of this, and so we had 3 existing foundations, as I mentioned: a 4-foot diameter drill shaft, a 6-foot diameter drill shaft, and then a 4-foot diameter drill shaft. And then we came in and we're going to put in some piles at the same location. And so this is just a Google Earth view of the site location and what's happening with it. We did SPTs, we did CPTs, and then we also installed some driven piles that were put in. Typical profile view of the site. Looking at this, it's the clay cap that I mentioned, overlaying silty clay, and then we have a liquefiable sand that's at a depth below that. The sand does start to get stiff with depth, and so there is just a zone of liquefiable material that we were interested in, and that's the target layer that we wanted to liquefy. So here's the site, just what it looks like. Have the 4-foot diameter shaft, 6-foot shaft, 4-foot shaft, and then back here, this is a H pile, steel closed-ended pipe pile that's been filled with concrete, and then a precast square 18-inch precast concrete pile. So the design load for this was 493 kips in designing it, just to make sure that we had capacity. We did that from a lot of different ways to find out what the capacity would be, different techniques for identifying what that design capacity would be. The down drag or the drag load, as we look at it, we want to make sure that we meet our checks for strength limit state and structural strength limit state. Both that was geotechnical strength limit state and structural strength limit state. So we're just making sure that we meet the checks. In doing these, we find out what's adequate, what's inadequate to make sure that we can carry those loads. The actual load that was imposed on the piles was 119 kips that was applied to the top of it. And so here we are, we're pulling the H piles off, closed-ended pipe piles off, and then the precast concrete piles. In placing those before we put them in the ground, because drag load is a depth-dependent phenomenon, we wanted to know how much load's developing in the pile as a function of depth. We put these strain gauges mounted onto the pile at different locations so that we can identify how much load is in the pile as a function of depth. To protect those during driving, we put on a 4-inch angle iron that was to cover all of the gauges as we drove them, to make sure that we didn't tear the gauges off during driving. This was interesting because there was a field splice that was performed, and so we had to make sure that we could go across the field splice. And so here are our strain gauge cables going across the splice, and then we needed to weld the pieces together. We also included strain gauge installation in the pipe piles. The pipe piles were driven without any strain gauges in them. And then we came in and placed the strain gauges into the concrete that was poured inside of the closed-ended pipe pile. And so that's how we got strain gauges mounted. We didn't have to pre-mount those. They were placed on PVC tubing, and then the concrete filled it in behind. And here you see the strain gauge cables coming out of the pile. Precast concrete piles were placed in a similar way. We put strain gauges, these are sister bar strain gauges that were placed in with the concrete during the fabrication of the precast concrete piles. There was also an Osterberg cell that was placed in one of those. We had one that was done with an Osterberg cell and one that was done without. So here are those piles coming out of the pre-stressing bed, and they were hauled to site. We had volunteer work done. This is Chris Hill Construction that did the pile driving for us out of Memphis, and just using a typical diesel hammer to drive these piles, and all of the piles were driven with the same hammer. Like I mentioned, all of them were driven with the same hammer. swinging set of leads there. So here's a splice for the H-pile segment. It's a Champion 3000 splice that was placed into it. PDA testing was also performed. So this is Travis actually out on site doing PDA testing for us. Thanks to GRL for doing that PDA testing for us. Typical results from the PDA, CAP-WAP results. And so I'm going to talk a little bit later about how the CAP-WAP results are very beneficial for determining down drag. You can actually use that as a precursor to identify how much load's going to be in the pile as a function of depth. And so we'll show how that matches pretty well with some predictions. So typical capacities after end of initial drive, both based on end of initial drive, and we did one restrike after 7 days on one of the steel pipe piles. Tight timeline, and so we weren't able to do restrikes on all of them, but we do have restrike on the pipe pile. Some setup possibly in what we saw here, just associated with the clay cap that we have there. And then the comparison with the capacities that we predicted from the different design softwares. After we got all the piles installed, we started loading them. These are beam blanks. So Arkansas produces a lot of steel piles. These beam blanks are the sections that are fabricated prior to them rolling them to get a typical H-pile section. These are 12,500 pounds a piece, and then we stack them on top of a loading platform that was placed directly on top of the pile. See a couple of cone rods that are placed in here. We had some dilatometers that were placed in the soil so we could investigate how the shear wave velocity changed after we liquefied the soil. So as I mentioned, 118 kips. It's really 119 kips after we place this top plate that adds as our distribution area. So those kips, the load was made up just with stacking these beam blanks on top. This type of testing has been performed before. In the past, it's been performed with hydraulic jacks that are acting as a reaction load. Oftentimes, after the liquefaction occurs, the hydraulic jacks can't keep up with the application of the load. And so we wanted to apply just a static dead weight on the pile so that we maintain the load during the liquefaction event. Prior to placing this in, we had drilled holes to drop charges into them to make sure that we could do that. So just we kept track using the strain gauges as a top-down application of load. After each of the beams placed, we can start to see that we haven't really mobilized a lot of the toe resistance, but we do mobilize skin friction as a function of depth as we develop that. So this is a typical look for a top-down, sorry, not top-down, but for unit skin friction change on how the soil starts to take the load as a function of depth. On the steel pipe pile, we developed a little bit more. It's a shorter pile, and so we were able to develop a little bit more load at the toe. So here's everything that's associated with this testing. Prior to installation of any of the driven piles, we did a pilot liquefaction test that was away from the site, still at the site, but away from where we were actually going to do the real testing, just to make sure that we can blast it, that we can liquefy it, and we can get recordings of everything that we need to know. How much soil settlement we have, what's the change in shear wave velocity as a function of depth, how much loss is there, or is there any loss associated with the soil following liquefaction. And so that was the first phase, just to identify what tools to use, and then the second phase is actually doing them around the foundation elements, and then we developed all that. So let's just step into phase one real quick. The different tools that we use to monitor what happened: piezometers to make sure that we liquefied it, to see what our excess pore water pressure ratio is. String potentiometers, these were used to measure the the surface deformation, and then vibration or a seismograph was used to make sure that we didn't cause any damage to the surrounding infrastructure. Because this is near a flyover, when we first started blasting, I was a little bit concerned that we might cause some issues associated with surrounding infrastructure, but we didn't see anything. The way that the blast charges are set up, it directs all of the energy into the location where the pile's in the middle of the blasting ring, and so we're forcing all the energy into the pile, not away from the pile. Digital level indicators to monitor how much the ground surface moves or how much the piles move, and then surveying stakes and Sondex tubes. The Sondex tube, this is used to monitor how the soil changes or the soil settles as a function of depth. And so I'll just show a couple pictures of that. So here's where we did the the free field blast to make sure that we didn't influence the location of the piles that we would be testing later. In doing that, here's what it looks like. We do some pre-CPTs and post-CPTs before blasting and after blasting. Here's the blasting ring that's set up. The piezometers are set up on 2 rings. We have an outer ring and an inner ring at different depths. These are redundant measurements, so we have 2 at each depth, one on the outer and one on the inner ring. That's 2 purposes. One, the directivity effect caused by the blasting. We could see more excess pore pressure closer to the blast or farther away from the blast. And so that's what we were investigating by doing these. Can't really do a nested piezometer because these are resistive gauges. And so each one of these is drilled and pushed in, and we'll talk more about that in just a second. So here's what it looks like, the blast holes. We had 2 decks of charges. The bottom deck was shot first, and then we would move up directly into the top deck. The piezometers as a function of depth in these 2 rings surrounding at different locations surrounding the piles. So these are the piezometers that were used. These aren't vibrating wire. These are resistive gauges. We don't want to have damage from the blasting causing too much pressure on our vibrating wire gauges. And these are able to be measured more quickly. Instead of the repeat time on a typical vibrating wire gauge, we can record these in a quicker fashion. We use some emulsion explosives, and so that's what's shown here. So the piezometer was placed into a plastic sleeve with a cone on it, and then we pushed that into the ground at different depths. And so we would drill out to a depth of 2 feet above the target insertion, and then we would push this into the ground and backfill with a bentonite slurry. Here's what it looks like. We have some Invar rods that are placed to monitor soil settlement as a function of time. And then we also have the string pot potentiometers that are loaded on some stakes to measure how we change. This is just one big string that goes all the way across. And then that's kind of a reference beam, if you will, that's being used to monitor that soil settlement. A lot of grout. Here's the CPT rig pushed in, ready to do the post blasting evaluation on how it changed. So here's the pilot liquefaction test ready for free field blasting. As you can see, sandbags paste over the charging. Because this is casing and we put stemming inside of the casing, when the charge goes off, it can shoot the casing out. So we need some dead load on top of the casing to make sure it doesn't shoot the casing out. We're trying to keep all the energy in the ground and not have any energy go out of the ground. Very close to an active roadway. Specifically, this is Interstate 55 going from Memphis to St. Louis, and so that's the proximity. We're about 200 feet away from I-55. So looking at the pore pressure response as a function of time, we liquefy, so our excess pore water pressure ratio gets above 1 for certain depths. For the clay cap up top, we didn't liquefy that, but we did liquefy the zone of interest there at about 11.3 meters. And we didn't liquefy at a deeper depth. And so we just liquefied the zone that we were interested in. So just zooming in on that, showing that we do reach a excess pore water pressure ratio that's greater than 1 in that liquefaction enough. But we didn't get it in other areas. And so that's just confirmation that we got liquefaction in the area that we targeted, and we were able to use that to measure what happened. So following liquefaction, the responding recompression, following liquefaction, we see that this bullseye develops around. So the piezometers would be located at the center, and then we just measured one side of this settlement profile. And so usually we see a bowl shape or a bullseye if we look at it from the plan view that develops following liquefaction. And so we're seeing that here, that we are seeing settlement of the ground surface. Looking at the pre and post blast liquefaction analysis, or the CPT results, we don't see a large change in cone tip resistance or sleeve friction. Some of this is just because these were done 5 feet apart, and so we didn't really see a reduction in the CPT profile at all. That's interesting as well, because possibly this could be done multiple times to be able to get data in it wouldn't affect the results if we do blast multiple times. Another pre and post blast comparison, just with some different depths that we have shown here, a different pair, if you will. So to do this, we want to make sure that we have liquefaction, and so we had to look at the literature to see, how can we generate enough excess pore water pressure. And so this is really us trying to figure out how much charge to place into the soil. And so anytime you're doing charge for liquefaction analysis, it's usually based on the scale distance. And with that scale distance, and when we look through the literature, we were finding that, there's not really many that are soil dependent. And so, in a couple of these, you can see that there's a relative density term that factors in. On some of them, there's a vertical effective stress term. And so we wanted to evaluate how this is done and whether or not these equations need to be modified so that we can get the excess pore pressure that we want without, overcharging the site that we have. So this is the one that we factored in the most because it had both vertical effective stress term, the relative density term, and then it also has a function of the peak particle velocity that's in there. And so this was a relationship that's been used in the past, and we wanted to focus in on that relationship. A lot of other ones talk about, what the scale distance is to get the peak particle velocity. And so we just did a literature review to make sure that we're finding the right stuff. And these are for all different types of soils. And so not just for liquefaction induced triggering, but also for other things like, tailings, and also just for blasting type of deposits. So in this Charlie 1992, it found some scale distances needs to stay less than 3, and the peak particle velocity needs to be greater than 0.16, and the peak compressive strain needs to be greater than 0.1 in order for liquefaction to occur. And this is probably the one that's the most cited, and so I just highlight that one because it's pretty commonly cited in the literature. We modified it. We came up with our own proposed empirical equation based on this free field blasting test so that then we could use this to be able to predict how much charge we needed to use for that. And so looking at the scale distance, this is the weight, and that's the distance from it in terms of a scale distance. Looking at it, we put 8 pounds of charge, and then this is looking at the inner ring piezometers and the outer ring piezometers. If I put 8 pounds of charge in, I can get excess pore water pressure of 1. And if I use 7 pounds of charge, I can get excess pore water pressure ratio of 1. And so to liquefy at the pile, I would need to use 8. And this is what we were looking at with those 2 inner and outer rings, that we do see more charges required to get the inner ring to liquefy. So now we're ready to move to phase 2 and start looking at how we actually did this with the full scale. Very similar soil and material properties. Very similar equipment was used to do this testing. Some differences, and we'll talk about those differences as we put those in. So this is what the site looked like when we did the driving for the project. And so on this one, we have a still age pile, a pipe pile, and a pre-stressed pile. Those are the 3 different depths, with the tips being at different depths just to get the same capacity. Piezometers surrounding each of the piles, and then the charges were placed in pre-drilled casing to set off the charges and monitor how we liquefy it. The groundwater table varies depending on the flooding stage of the river, because this is tied to the river levels, and so it changes anywhere from 0 to up to 15 feet. And so that's what's shown here. The liquefiable layer, sorry, let me go back one slide. The liquefiable layer did remain saturated, and so that's what we needed to have happen for the testing. So the way that this was performed is that we would blast one of these at a time. And so I would use whatever load was on this pile, I would move it before the next load so that we didn't have to have loading on each of these and blast each of these sequentially. So the first set that we blasted was the H pile. Then we moved the load to the pipe pile. We blasted the pipe pile. We moved the load to the pre-stressed pile, and we blasted the pre-stressed pile. This is just showing how we drilled a Sondex tube. And so a Sondex tube, it has metal bands on corrugated pipe at different depths. And then it has a center PVC that goes down through the middle of it that you drop the tool down. And so this gets installed to depth. We use the PVC pipe to actually push in the corrugated pipe. goes all the way to depth. And then as the soil grabs onto the corrugation and moves it down, we'll be able to see these bands changing location as we go down from a given reference top of the PVC that the tool goes into. Here are the string pot potentiometers measuring amount of deformation. The load that's shown here, this is actually the load that's on one of the drilled shafts. And so we had drilled shafts next to driven piles. I would blast one shaft and one pile with a given event. And so we did 3 events, 4-foot pile and 4-foot shaft and H pile. Then the second event was the 6-foot shaft and the pipe pile. And then the last event was a 4-foot shaft and the precast concrete pile. Also had some Leica digital level rods to measure how the surface, or how the actual, in this case, the drilled shaft top moved, both during preloading and then also during blasting. Using, from a standoff distance that's not moving, we can monitor how the foundation height is, or the top is moving. So here's just an example. We're outside of the blasting zone. We've got our surveying level to look at how the ground surface is changing. We're also looking at a Leica rod that's on the pile to monitor how the pile top is moving as well, in doing it with this setup here. Again, we used emulsion explosives. This is a dyno AP that was stacked. So we installed the casing beforehand, and then the blaster would come out on the day of the blast, lowered in, and then we used just sand stemming behind each blast. And so we would drop the required amount of charge, 8 pounds of charge for the bottom deck. We would put stemming in, then the top deck, then more stemming, and then we would top it off, or place sandbags over the top of it to keep the energy in the ground. So as I mentioned, this is how it was done. We did a figure-8 pattern for each blast event. And so the first blast event, we started near the north shaft. We work our way around that. That's directing all energy into the north shaft. And then we work our way around the H pile. That's directing all energy in to the H pile. Each one of these charges was offset by 500 milliseconds. And so this charge would go off on the bottom deck. 500 milliseconds later, that one would go off. And so it would work its way around. Then we would go with the top deck and work our way around as well. So we do the north shaft and the H pile, center shaft and pipe pile, and then south shaft and the pre-stress pile as 3 separate blast events. This is a video that shows the blasting, and so this one was done for the center shaft and the pipe pile. We have some surveying instruments that are set up outside of the blasting ring. This is the data acquisition for the strain gauges that are set up as well. And then there's a couple of cameras that are at different locations. And if you guys have time at a different time, there's some videos showing how we did this blasting if you're interested in more information. We weren't able to get the sound to work on this for the video today, but if I do hit play on it, you can start to see in just a second, each of the blasts go off. And so we're going to start a figure-8 pattern that comes around it, and it goes pretty quick because it's only a 500 millisecond delay. If you keep an eye on the hook of the crane here, when the blasts start, you'll start to see that there's a pretty significant amount of energy that comes out of that. And so we blasted as we were going through. And so there's the blasts that are going off, worked our way around, then we came back around with that, and the hook of the crane is swinging. As I mentioned, there's a video online that shows it a little bit better, and it's easier to see when you can hear the actual charges going off as well. So excess pour water pressure, we were able to liquefy at a depth of 9, 10, and up to 11 meters. And so we got the zone of interest. Most of these spiked either right at 1 or very close to 1. A couple of them went over 1 with that, even down to 14 meters. And so we got the zone that we were interested in. For the closed-ended pipe pile, we didn't get as much energy into it, but we still did liquefy the zone of interest based on excess pour water pressure ratio measured with the piezometers. And then also for the pre-stressed concrete pile, we were able to get liquefaction. Note, this is very rapid. We were able to reduce those pour pressures very quickly, but we liquefy the zone, and then we do see post post liquefaction response in the soil settlement. So here's just an example of how much settlement we had. We spray painted the soil next to the foundation just to see how much soil settlement there was at the location of the pile. And so for the south drilled shaft, we saw about 3 inches of soil settlement relative to the location of the, in this case, drilled shaft or driven pile. For the pre-stressed concrete pile, we saw about 1.5 inches. And so this could be size effects that are causing a little bit more changes there. Here we're looking at different times during the blasting, how much surface settlement we have. And so we see that we came out, we measured surface settlement, and we came back, later and we get surface settlement. And so we do see a little bit more settlement as a function of time as the soil is settling. So that was for the, sorry, let me go back one slide. This is for the H pile, and looking at the pipe pile, we do see settlement change between 30 and 330 minutes. And so this is leading to down drag, the amount of settlement, and then also the amount of settlement would lead to some drag load that develops within the pile. And then here's the pre-stressed concrete pile at different times, so 20, 80, and 750 minutes after the blast. So in plotting this, looking at the still H pile, this was the curve that was developed immediately after we had all of the dead load placed on top of the pile. And so this is the load shed as a function of depth caused by that top load that's placed on top of the pile. Caused by blasting, when we look at this, we see that we do develop this neutral plane to develop. As I mentioned, this would be like the load curve that I talked about before, the resistance curve. This is my in bearing. And then this value here at y equals 0, that's the top load that's placed on it. And so based on the neutral plane theory and what we saw in the measured strain gauges, we see that a neutral plane develops about 17.98 meters. So that's for the still H pile. If we move on and we look at the pile settlement, so on the pile, we have elastic compression that's accounted for, and we have top movement of the pile. We see the pile settlement curve, and then the soil settlement curve. This was done using the Sondex tubes, and so how much the soil settles is a function of depth. We see that the neutral plane develops based on the intersection of soil settlement and pile settlement at about 18.2 meters. So pretty close. It was neat to see that these responses were very similar in the fact that, this is what we had predicted and this is what actually happened from that response. So from that, at a time of 180 minutes, we saw a drag load develop of about 306 kilonewtons. And that would be a load that we wouldn't have developed, or that we wouldn't have accounted for if we didn't take into account the drag load that we had. For the pipe pile, here's the resistance as a function of depth. Immediately after we place the top load onto it, so that's the dead load that's placed on it, we blast and we see that we have a neutral plane developed. Note, 2 of my strain gauges died due to the blasting charge being too high, and so we lost these 2, but you can infer that it's moving down and then moving back in what we have going on there. Looking at pile settlement for this one, again, we see this curve. We predicted, or we measured the neutral plane using the load approach at 18.44, and then we measured it at 18.90 using the settlement approach. So in this one, we accounted, or we measured a 415 kilonewton down drag load that developed, and then the amount of down drag that we would have would be about 10 millimeters because it's at the location of the neutral plane. Last case is the pre-stressed concrete pile. For this one, we didn't have a preloading curve. It rained that day very intensely, and so we weren't able to get the preloading on that setup. We were trying to move between sites, and we were moving the beam blanks, but not able to record the top-down load change as a function of time. But we do see a neutral plane develop at a depth of 18.3 meters using the pre-stressed concrete pile. And then using the settlement approach, we see that depth at about 19.8. So this one didn't match as well, but we are still about 1.5 meters or 5 feet difference, and are able to use that information for design. So we developed 306 kilonewtons for the in this case, the pre-stress pile. And note, different piles had different amounts of drag load that developed, caused by, one pile being deeper and more positive friction below the liquefiable zone than the other ones. And so that's why we have a difference and also difference in cross-sectional area, causing a different amount of load to be developed. So just looking at how much down drag was measured versus how much down drag was predicted, and then also how much the neutral plane is different than what we had based on the predicted AASHTO design method. We did that for the drilled shafts and also for the H piles. In doing that, we may not predict or measure some of these very well, and so some changes were needed based on the outcome of this result of the research. What we found, I used the program P.H.D from Bridge Software Institute to do a lot of the prediction curves. And so if I had used that program, we need to modify the load curve by about 30% in order to predict what we would get out. And so just looking at these two curves, there's a 30% difference if I use the P.H.D software program to predict the amount of load as compared to what we had. And so by modifying it, here's the measured and predicted with that 30% modification on the amount of load curve that's there. And so we see that. But what's really interesting is, and I'm going to talk about this here in just a second, that if we look at the CapWAP analysis, we can actually predict that with a CapWAP analysis. And so that's a neat thing to know. Trying to get the cursor up here. Okay, so it's just some conclusions and recommendations that we have out of this. The in situ properties were affected by the dissipation of excess pore water pressure. There's no decrease and increase in friction caused by the blasting, and so we could reblast if we wanted to do more tests than just one. Modify empirical approach for RE was developed and proposed, and so if you're going to do some blasting, that's a good modification that we put out into a journal article. From the blast-induced liquefaction testing, the neutral plane moves from being at the top of the foundation before liquefaction to right at the top of the liquefiable layer after liquefaction occurs. Before blasting, no negative skin friction was developed, but then after blasting, we do see it. So the reduction in side goes from 100% resisting to 50% contributing is what we observed. And then the neutral plane moved to the bottom of the liquefied layer. So some just recommendations and conclusions that we have here, specifically related to the in situ conditions should be used to determine the blasting layout. Proposed method used to estimate post-blast load and resistance curves, so you can do that before you blast and then compare them. And then this was all on single piles. And so we think that there needs to be an extensive study on a pile group. And I'm going to give it away, but we've already done this. And so I'm going to talk about that here in just a second. The mechanisms on what's leading to the liquefaction-induced down drag and drag load should be further evaluated, is what we also said with the conclusions. So this is a different study still in Arkansas. Nucor Yamada Steel, they're the ones that made the H piles and pipe piles for the previous testing and gave us the beam blanks for that testing. They're steel plants in Blytheville, Arkansas. And so they provided us the opportunity to come out to their site. They were constructing a new addition onto a galvanizing plant that they have. And they already had the crane on site. And so they told us that we can come out and drive some piles for them. And so we drove a pile group, and we actually drove two pile groups. One's an H pile group, and then the other one is a pipe pile group. So the H piles that were driven, within this cap here, there's 7 H piles that are 14 by 102s that are 85 feet long. And then behind this, and I'll show you from a different camera angle here in just a second, but you'll see some pipe piles that are 18-inch in diameter that are driven closed-ended and filled with concrete. So I just want to show you another blast that we did. And the reason for showing this is I want you to see how much surface deformation occurs following it. Also keep in mind that if you look at the actual pile cap, the pile cap doesn't move a lot. And so let's look and see what happens just following this blast that goes on. So the camera is shaking right now because the blast is occurring. You see the blast going because the sandbags are moving. We work our way around. That one actually shot out a little bit there. Here, these orange circles with pink flags, that's how we're measuring surface deformation as a function of time. So if I just take this back in time, you see the ground surface now, and then if I move this back in time, you can see the ground surface actually change in depth. So we do see movement of the ground surface. I'm going to go to the next slide. It shows it a little bit better. It's from a different vantage point. Sorry, that's not the next slide. Yeah, this is just a rendering showing how I sped it up just to show. So there's three, it's like a GIF, if you will. There's three different pulses just so you can see how much it moves down, comes back up, moves down. That's just showing you a GIF animation on how much surface deformation is occurring to the visible eye. So here are those two piles looking from a different viewing angle. Again, this is 1.5 million pounds of dead load that's placed on it. Those are the largest beam blanks they make. So each of those is 50,000 pounds that's on top of this. We have the pile group. Here, if you're seeing these small, those are actually displacement transducers that are measuring the amount of soil deformation at different depths using Boros anchors. And then we have an Invar rod here to measure how much the pile moves, the pile cap moves with that. So some surveying measurements that are out here to look at that. So I'll show this blast from this angle just to see it in a little bit different viewing geometry or viewing angle. What ends up developing is we start to see some ejecta that actually came out of the ground here. Going to the next slide and viewing it again quickly, kind of as a GIF, just to see the amount of soil surface deformation that occurs. Sorry, that one wasn't the GIF, I don't think. That's the GIF that shows up there. You can see kind of the pumping. So this is after liquefaction is developed. And then just to see the amount of soil movement that's associated with it. It goes down. I restart the video, it goes down, or restart the video. That's what you're seeing there. So we saw about 7 inches of ground surface deformation associated with the blasts with this, and we didn't really see a lot of movement of the piles, of the pile group, or the piles that happened underneath that loading. And so just trying to look at how the group effects interact with it, and this is an ongoing study that we're turning out results on now. And so I don't have a lot to share on it. I just wanted to show you that this is something that we're doing. Moving along on how to design these, I've got about 9 minutes left and have 8 slides. And so in part in this testing that we did with developing new codes for Section 3 and Section 10 of the AASHTO code, we tried to find a way to do a design example that would show, practitioners how to develop this. And so looking at the site at Tyrrell, I used the CPT profile, and I went to a program called All CPT. This is a program from Innovative Geotechnics out of Perth, Western Australia. And so you can input your CPT data and it will process it and give you all the different correlations that you could possibly need for doing these types of analysis. But what's nice about this is you can do it pretty quickly, right? Input the CPT data. After I get the CPT data input, it gives me my typical plots that I would need to do some kind of pile capacity analysis. And so the pile capacity analysis that it has within the software is I can do the LCPC method. And so I'm doing the LCPC method using a driven metal pile, both the identifiers for group 1 and group 2 in doing that. So it automatically will do the LCPC method for you, and I can get a capacity out of that. So this would be my ultimate capacity that I would get from that design software package. Using that information, the output table or the output results that we have, What I'm interested in, I'm going to come in here and find out how much skin friction I have as a function of depth at each depth, right? So this would be, if I find the difference between these two, that's the unit skin friction over that sublayer, the unit skin friction over the next sublayer, unit skin friction. So I can use the output from this table. Sorry, this is the actual unit skin friction, and then QLS is the cumulative as we work our way down. I also need to know the in-bearing resistance. And so from the output table, I get QB and I know my in-bearing resistance. Using that in-bearing resistance and the amount of unit skid friction as a function of depth, because my pile was 22.55 meters, I used that in-bearing resistance at that location. I can plot up my curve, and I'm going to show that on the next slide. But in addition to doing that, I can also develop a top-down load displacement curve. And I need that load displacement curve to both find the geotechnical capacity and also to find out how much toe movement is going to happen from this pile. And so because we're going to compare both the toe movement and the in-bearing capacity, I need to know that. So let's go back real quick. Within this pile capacity, in order to get the top-down load settlement curve, I need to know something about soil stiffness. And so the soil stiffness came directly out of that same output that we had from the CPT. If I just come over here, there's a column for ES. And so that's my soil stiffness that I can use in the design software program to be able to develop this top-down load curve. It uses Fleming's approach. This was an approach that was presented in 1992. And it does a good job of developing a top-down load curve. So looking at the top-down load curve that was developed out of the software program, plotting on Davidson's criteria, we see that we get a pile head movement of 23 millimeters and a design geotechnical capacity of 2650 kilonewtons. And using that information, I can then develop my cumulative load displacement curve. And so what we're seeing here is I have load resistance. So this curve was developed by plotting all my loads, and that this curve would continue on here, and then plotting all my resistances, and that curve would continue on there. But I'm just going to plot the minimum of those two. And so I see this curve where I'm on the load curve until the neutral plane, and then I'm on the resistance curve until the toe of the pile. So the in-bearing resistance came directly, that was the QB that was mentioned. So that's why I highlighted that QB. And then the unit skin friction we're adding on from the toe up. For the load curve, I just take how much top load I put onto the pile, and then I add in my unit skin friction as a function of depth. And so where those two interact, that would be my neutral plane. The drag load that develops is the peak load in the pile minus the top load, unfactored top load that's placed on top. And so that would be the drag load that we would have to design for. So if I use that drag load, we're making modifications to the code right now that say that we're probably going to multiply that by 1.1 instead of 1.4 based on some results that we've gotten out of Minnesota. And so there will be some changes to code on how we handle this drag load and what we do with it. The down drag also is of interest. The down drag is the settlement at the location of the neutral plane. And so from the settlement analysis, I see that I had a movement of 19.3 millimeters at the neutral plane. This curve that's shown here in black for the soil sonar, that was a measured curve that we had from the field. And so that was based on the Sondex tubes that we had at Turtle. And then this pipe, that load came from the previous curve, or that movement came from the previous curve. So that's my top movement. I put that in, take into account the elastic compression, and where those two interact, that's the location of the neutral plane. So the locations of the neutral plane are within 0.8 meters of each other, and that's good. If that number is usually within 5 feet, we can take that, say that that's a good result. Something to take away. If you wanted to predict it, so we're using just typical design procedures to predict it, we could also have a verification at the time of driving. And so if I did a CAPWAP analysis, from the CAPWAP analysis, I can see that I get drag load that's very similar to the drag load that was predicted. Although it doesn't follow perfectly, it does follow pretty well. Note the neutral planes based on this approach are a little bit different. Also, the CAPWAP approach, if I develop that, so here's the predicted from the all CPT program, here's the CAPWAP predicted, and then here is what we had following the blast. And some of you might be saying, hey, we don't get as much drag load as we thought that we were going to get. And the rationale for the reason why we don't is because the blasting curve didn't mobilize the full end-bearing resistance. And so this curve is shifted to the left because of that. If I had mobilized the full end-bearing resistance, I would be able to get there. And so the recommendations that we're making in the code right now are to use a TZ analysis. And so, for instance, the program TZ Pile does a really good job of predicting that. On this, for the prediction from the combined load resistance, that's done for a fully mobilized pile. And then if we think about what's happening with CapWAP, we're also fully mobilized when we're striking the pile. And so that's a good analysis for fully mobilized. But if we're not fully mobilized, we might need to use a design software program like TZ Pile, where we're taking into account the partial mobilization of both the unit skin friction and also the partial mobilization of the tip resistance. So that is one design example that was based on what we did at Turl. The other design examples are based on the work that we did at Blytheville for that pile group. And so around January, we should be coming out with that NCHRP synthesis that we'll talk about what we have going on. But I can't really talk about it yet until we're done with that. I'd be remiss if I didn't mention the sponsors. These are pretty big projects for a professor to do. And so it's not without the help of people like DFI, reaching out to some of their partner members to help. All these people were very influential in what we did. As mentioned, Chris Hill Construction did the driving for us. RDOT sponsored the research. AFCO still provided the top plate for the loading mechanism. GEI came in and did some cross-hole sonic for the drilled shafts. Nuclear Armada Steel donated all of the steel that was done and the top load that was placed. MoDOT did all of our CPT testing. Cold grading did the blasting. ICE provided the hammer and the helmets for us to be able to use. Applied Foundation Testing provided some Osterberg cells that we put into some of the piles. Texas Concrete Partners provided the pre-stressed concrete piles. GRL did the PDA testing for us, and DFI kind of helped offshoot this and everything that we did. So I thank all the sponsors. With that, I welcome questions. I want to hear what you guys have to think about the program, and I'll open it up for that.
Thanks so much, Ray. It's quite a big group of sponsors you brought in, huh?
Yeah. Couldn't be done without them. Really appreciate all of them.
Yeah, if anyone has any questions, please pass those on in the chat. We have a few more minutes here with Rick. Why do you do the charges in sequence instead of all at once?
Yeah, we're trying to get the energy directed, and so when the charge goes off, it'll build up a little pore pressure, and the next one follows and follows. If we go all at once, sometimes it's a pressure shock that's too large for the instruments, and so we can gradually accumulate the pressure rather than just really shocking it all at once.
Mm-hmm. Oh, there's a question. Can you see the chat?
I don't have the chat
you can't see it?
in front of me. Wait just a second. I might be able to see it in just a second. All right, let's see what we have here. Chris Lynch.
Oh, I guess no one else can read this. Given recent research.
Yeah, you go ahead and read it out to everybody.
Okay. Given recent research into the effects of small and large shear strain history on liquefaction resistance, can any observations be made on the liquefaction magnitudes for the different test piles from the first field test, considering consistent charge size and geometry, phase charges, and initial pilot charges? And if you can read that, I'm sorry that I
No, it's good. I got it. I probably should have read it. It's tough for me to understand as I'm reading it, so I wanted to have you read it and then I can understand it. Looking at what we have here, we were trying to do that with the RU equations, and so we knew what we had developed. We knew the amount of excess pore pressure developed from the piezometers, and then we tried to use an equation to predict that. And so I think that's getting to some of what you have there. In terms of the shear strains that developed, we only had the one seismometer, and so we didn't do a lot of work related to what was happening with the small and large strains that were developing in it. I didn't have any kind of instrumentation to monitor soil strains or anything like that. What we're really interested in is the global, not the the global response, not the individualized layer response. And so hopefully that answers your question. If you got more, please reach out to me and we can talk more offline. Gary said, have you summarized the findings in a paper? There's been a couple of papers that have been out. There are more that are forthcoming. Some students are writing some stuff up now. And so the one that dealt with P.L.S was done at a conference in Norway that turned into a journal article. And then there's a couple of masters. There's a master's thesis. Kyle Rollins was one of my co-PIs on the project. His student wrote a master's thesis on the driven P.L.S, and then my student wrote, my PhD student who works for Travis now, Elvis Shimwe, he wrote his dissertation on the driven chefs, the drilled chefs. So if you want to reach out for any of those or need that information, just send me an email and I'd be happy to pass that on.
Rick, I see that there's no change in strength between pre and post test on the CPT.
There is no change
How's that possible if it settles?
Yeah, we've seen this happen with some others. I think it's caused by possibly. So I'm going to go with some possibilities here. When we blast, there's some gas that's developed, and so the gas could lead to expansion, and so it actually causes the soil to uplift before it settles back down. And even with the settlement, we're settling into a similar state. We're not getting more dense, and so we're just seeing the same strength based on CPT results. We're seeing the same strength that we saw beforehand. Had another question.
Did you expect to see a change?
I did. I thought it would be more dense, but it definitely wasn't. And now that we've gone back and looked at some other blasting that's been done, Armin Studlin did some in South Carolina. I think he saw similar results. Kyle Rollins has done some in other locations and saw similar results where we don't see an increase in shear strength associated with the blasting, even though we have some reconsolidation.
So how's it not more dense if it settles? Sorry to keep.
Good question. Good question. It just isn't based on what we see.
Okay.
I mean, the soil is more dense, but we're not seeing an increase in shear strength or an increase in capacity, both in terms of tip resistance and skin friction from the CPT.
Okay. Okay.
Yeah.
David asked if the CapWAP analyses included residual stresses.
That's an answer. Travis, what do you think, man?
I don't have it in front of me to look. I sort of suspect not. They're
I don't
not
think they do.
that deep, and they don't have very high blow counts. So I would not think so unless you specifically had a reason to direct that.
Right. The residual stress questions come up quite a bit in a lot of the work that we've done on how residual stress affects what's happening with the down drag. It's something we're still working with. We tried to predict it and try to understand it more with this project, and we weren't able to. And so it's still a question for, ongoing discussion and ongoing debate.
There's another question about developing the pile settlement curve. I don't know if you have the quickest way to
Now the pile settlement curve is developed. Yeah. Let me see. Can I just get out of this and go back to the main? Oh, no,
you lost control.
No, I still have control, but I'd like to just be able to go slide sorter if I could. Kevin, can you make that happen? Yeah, fantastic. And then now I have control of it again. Okay, let's go all the way back to this slide real quick. And there's a video on YouTube that we put together that shows how to do this as well. And then can I go full screen with that real quick? All right, I'm gonna get to a point where I can draw this up and just have kind of everything on it. So the first thing that you do to develop this combined load settlement curve, I have to know the toe resistance. Then I take a summation of unit skin friction as a function of depth, and I'm going to sum from the bottom to the top. Usually we're used to summing that up from the top to the bottom. That's how the load curve's developed. And so the resistance curve is my toe resistance plus the skin friction cumulative as a function of bottom to top. And then the load curve is unfactored top load plus the unit skin friction as a function of depth. So if I wanted the combined curve, what I would have is top load plus the unit skin friction until I reach the intersection with the resistance curve, and then I would use the resistance curve. And so this would be the combined curve that we would use for design. And the drag load that develops is the amount of load at that intersection minus the unfactored top load that's on there. So I have that shown just in some more animations here. Note, soil settlement, this can be measured with those either from Toros gauges or from Sondex tube. And then the pile is measured at the pile tip, and then we take into account the elastic, or at the pile head, and then we take into account the elastic compression. So there's the drag load, and then the down drag should actually be this settlement that's right here, however much settlement that is. I have it shown here as being down drag, but it should really be at the neutral plane. That answer your question? Any other questions?
We'll have to hope so.
Any others
I
that I
think
can
we're
answer? Pushing on time?
just about out of time too. So
Okay.
as the slide says, PDH certificates are available if you paid to attend and get that certificate. And then as far as further impact webinars, I think the schedule's in a little bit of limbo for 2024. So stay tuned for when those will come again. Thanks so much for the time, Dr. Coffman.
Yeah, thanks for the opportunity. Really appreciate it.
Interesting. I'm going to think of some more questions and probably shoot them to you
Sounds
shortly
great.
as I look at it closer.
Yeah, if anybody has any questions, just send them to rick@uark.edu. Thanks so much for your time, guys.
Thank you.